play snooker, I need a knowledge of what happens when billiard balls collide. And this relates directly to Newtonian mechanics. But of course, there's the human factor of skill and judgment as well. But when I'm potting a ball, I'm certainly not consciously applying Newton's laws. Yet my common sense feel for the right angle is in complete accord with Newton's principles. Well, in this program, we're going to explore an area which is far away from classical mechanics, far away from Newton's laws, and where our common sense notions aren't going to be much help to us at all. Well, what area am I referring to? Certainly not phenomena on the scale of the solar system. After all, Newton's laws work extremely well. We can predict precisely eclipses and so on. Nor is it the world of our everyday surroundings. Newton's laws work fine there. No, it's the realm of the atom where our common sense notions let us down completely. Yet physicists did, for a long time, try to extend classical ideas right down to atomic dimensions. And the Bohr atom is an example, with miniature billiard balls orbiting around. Well, atomic physics is much more fascinating than miniature billiard balls. We'll need to bring in entirely new ideas far away from our everyday experience.
But first, let's try to get things in perspective by looking at the kind of distances and speeds that we measure when we do physics experiments. The distance scale is logarithmic. It ranges from these astronomical distance scales right down to the subnuclear region. Let's get our bearings. 10 to the 13 meters is a reasonable estimate of the distance across our solar system. And at the other extreme down here, there's 10 to the minus 14 meters, which is roughly, within an order of magnitude, the distance across a nucleus. Now, the speed axis is also logarithmic. It ranges right up here to about the speed of light, about 300 million meters per second. Obviously, we can put an awful lot of observations on this diagram, but if we're only concerned with our everyday experience, we can concentrate on a much smaller region. Now, in the everyday world, we come across distances ranging from, say, about 10 to the minus 4 meters, the distance across a speck of dust, right up to, say, the distance you can see to the horizon on a clear day, about 10 to the 4 meters. Now, the speeds we come across will range up to, say, the speed of a very fast jet aircraft, about 1,000 meters per second. So this, then, is the area of our everyday experience. Now, it's quite a small part of the diagram. Remember, both the scales are logarithmic. But it's a very important part because it's observations and experiments we make here that determine our common sense view of physics. Now, our common sense ideas are well described by Newton's laws of motion and other classical laws like that. But as you saw in the relativity unit, these ideas aren't quite right. And they fail completely up here at very high speeds, where we observe relativistic effects. Now, here we have to use a special theory of relativity, not really a common sense theory, but we have to use this theory to understand phenomena in this region. Now, there's another region of the diagram where our common sense lets us down again. It's over here, in the subatomic region. Now, here we observe quantum effects, which we can only understand if we use quantum mechanics. Now, quantum mechanics is not really a common sense theory of nature, but we have to appeal to experiment to see what features this theory will have.
Here are some tracks produced by particles like electrons and protons in a device called a bubble chamber. They're certainly suggestive of tiny particles following definite paths as they fly across the chamber. And you can also probably see that they're bent around. That's because the whole chamber is in a magnetic field. And if I measure the curvature, I can use the laws of classical physics to work out the momentum of each particle. In fact, you've used just this idea in a summer school experiment, the magnetic field experiment. This is the apparatus you used. And if I turn on the magnetic field, you can see the electron beam being bent just like the particles in the bubble chamber. Well, so far, there's nothing to suggest that the laws of classical physics can't handle all this. But take a look at this apparatus over here. Here's a similar sort of tube with an electron gun, and the electron beam hits the phosphor screen here at that spot. And I can move it around with a magnetic field from this tiny bar magnet. But now suppose I were to put this very small metal foil in that tube just downstream of the electron gun. Now, what effect do you think that would have? Well, I can actually do that experiment because over here I have a tube with just such a foil installed in it. So let's dim the studio lights, and I'll turn up the voltage on the electron gun. I'll do it just once again. And there you can see this beautiful ring pattern, undeniably a diffraction pattern. But these are being produced by electrons. Yet I can only explain that in terms of a wave phenomenon. In fact, if I measured the position of those rings and I knew the spacing of the atoms, I'd be able to use the diffraction formula to actually work out the wavelength of the electrons. But what does it mean, wavelength of an electron? After all, a moment ago, I was talking about them in terms of particles. And those particle properties haven't gone away. If I were to turn down the intensity of the electron gun, you'd find that individual electrons leave the gun and individual electrons arrive in different parts of the ring pattern. It's just that the intensity is so large that normally the huge number of electrons evenly illuminate the rings. But now our classical physics really is in trouble. It can handle things like particles or behavior like particles. It can handle behavior like waves. But it's in difficulty explaining what happens with electrons behaving like waves and particles. So where do we go from here? Well, maybe we should look at the connection between the momentum and the wavelength of an electron.
The electron's wavelength is given by this formula, which was first written down by Louis de Broglie. It says that the electron's wavelength, lambda dB, is equal to h divided by the magnitude p of the electron's momentum. The constant h is, of course, just Planck's constant. It's a constant that crops up in practically every equation in quantum physics, although it never occurs in classical physics. Well, there's an important point to remember about this equation. It applies not only to electrons, it applies to any particle with momentum p.
Well, here's a moving billiard ball. It's certainly got momentum. Let me apply de Broglie's formula to it. Maybe it's got an associated wavelength, in which case I should be able to diffract it, just like electrons. And here, in fact, is a diffraction grating, regularly spaced slits about 20 centimeters apart. So let me fire this billiard ball along the center and see what happens. Well, just as you'd expect, I think, they went straight down the middle. Quite different, though, from our electrons. Remember how they diffracted in our earlier experiment with the tube. Well, why didn't I get diffraction effects with billiard balls if they have an equivalent wavelength? Why didn't they arrive on either side of the pocket, giving the usual pattern of maxima and minima? Maybe we should put the numbers into the de Broglie formula. Well, what's the mass of a billiard ball? Say 4 ounces, about 100 grams. So I have m equals 0.1 kilogram. And if I say the speed is about 10 meters per second, v equals 10 meters per second, then I can work out the momentum, and it comes out to be 1 kilogram meter second minus 1. Now let's use the de Broglie formula, lambda equals h over p, to work out the equivalent wavelength. Well, if I put in the numbers, because h is such a very, very small number, then lambda works out to be 10 to the minus 34 meters. Now that's an incredibly small wavelength. Let's see what the equivalent diffraction angle is. This is the formula I need for diffraction. Lambda equals d sine theta. Remember that d is the slit spacing and theta is the angle of diffraction. Here's the first order diffraction here. Well, again, if I put in the numbers, I'll find that theta is about 10 to the minus 33 radians. Well, that's a fantastically small angle. And what that means is that these various orders of diffraction all get squeezed into an infinitesimally small area around the axis. So small that we'd never ever be able to observe them. And the important conclusion is that these everyday effects don't actually contradict the de Broglie formula. It's just that for the everyday world, we don't have to be concerned with wavelengths of objects like billiard balls at all.
But we do observe wave-like effects with electrons. As John showed us, they're diffracted. And when we do experiments like this, we find that the wavelength of an electron is given by the de Broglie formula. Well, electron diffraction is a purely quantum effect. We can't explain it using classical physics. So now let's move on to look at another way in which classical physics and quantum physics part company. When billiard balls are set up like this, I know that if a ball comes in from this direction and hits the blue just tucked in behind the yellow, then both of these reds will be pocketed. Well, it wasn't just because I've seen it before. The result's entirely predictable on the basis of classical mechanics. If I came back next week and played the same shot, we'd get exactly the same result. Well, this idea of predictability is really just common sense, and it's completely basic in classical physics. If you do an experiment and get a result, then if you come back later and do the same experiment under the same conditions, you must get the same result. Well, this idea of predictability certainly works when we're playing billiards with ordinary billiard balls. But what if we were to try to play the game with electrons instead?
Well, here's my electron billiard table. You probably recognize it as our familiar diffraction tube. So let's pursue our billiards analogy, but sticking strictly to what we can observe with real electrons. At this end, instead of a billiard cue and a diffraction grating, I've got an electron gun and a thin metal foil. And over here, I want you to imagine that I've got a pocket for catching electrons, in reality some kind of electron detector. And as the electrons come along the axis, a lot of them do go into this pocket, but they also end up on these beautiful diffraction rings. Well, now let's concentrate on what's happening in the plane of the table. In fact, imagine that I've got a whole array of pockets spread out on either side of the central pocket. Then I'll get a lot of electrons being caught in pockets in the bright areas, here and here, and very few or no electrons in these dark areas. What I've got, in fact, is my usual diffraction pattern with peaks and troughs. The central pocket is here, with the other pockets on either side. But now I want to ask a very important question. Suppose we consider one particular electron from the electron gun. Into which of these many pockets will that particular electron go? Well, it seems a simple enough question. It's the kind of question that classical physics answers for us all the time. And I can certainly say that it's got a greater chance of going into a pocket in a bright area, corresponding to a peak in the diffraction pattern, than in a dark area corresponding to a trough. In other words, a bright area means higher probability. And if we think of that in terms of our diffraction pattern, it means that it's not only telling us about the numbers of electrons detected, but it tells us directly the probability of where the electron will go into which pocket. But I still haven't answered my original question. Into which one of these pockets will it actually arrive? Well, it turns out that for objects like electrons, the very best I can say is something in terms of probability. I just cannot predict where an individual electron will arrive.
Well, so it seems we're in much the same position as a roulette player. I can't normally predict where the ball's going to end up, but I do know the betting odds that the different numbers will come up. In the same way, when we use quantum mechanics to analyze an experiment, even if we know the possible results, we can't normally predict the outcome of the experiment. All we can predict are the probabilities that these different results will come up. In this way, quantum physics differs fundamentally from classical physics, where we deal normally with certainties, not with probabilities. Well, quantum mechanics is a very remarkable theory because it enables us to incorporate this idea of probabilities, and it also enables us to come to terms with a wave-particle duality. But before we can go into any more detail about how quantum mechanics works, we need to look at the properties of waves in general. This is an ordinary sine wave travelling along the positive x-axis. It could really be any type of sine wave, for instance, a pressure wave or a water wave. If we take a snapshot, we can easily see that it has a sharply defined wavelength, lambda. Now, there's another important quantity we can use to describe the wave. It's called the wave number, and it's denoted by the letter k. Now, the wave number is equal to 2 pi divided by lambda. Now, there's no new physics here. This is just a definition, and you'll see why it's useful in a moment. But let's go back to the snapshot and draw below an axis on which we can mark wave number k. Now the wave number of that wave, that's 2 pi over lambda, is marked here. Now the height of this line is equal to the amplitude of the wave. Well, now let's consider another wave. Now this one has a different wavelength, so it has a different wave number. And the amplitude of that wave and the one before are different, so they have different heights here. Now we can combine these two waves using the principle of superposition. There we are, as the bottom one's being wiped off, the combined wave is appearing along the top. And it's no longer a simple sine wave there, it's very localized though in this region here. Now we can go on to add a third sine wave. This one has a slightly higher wave number and it has a different amplitude too. Now when these waves are added together, we get an even more localized wave. Well, obviously we can keep on doing this, adding more and more sine waves. And here, many different waves have been added together to form a very localized wave here. It's called a wave packet. Now, to make up this wave packet, we have had to use very carefully chosen wave numbers and amplitudes. And that's a very important point. Now, these ideas are completely general. They apply to any type of sine wave. But what's all this got to do with quantum mechanics?
Well, let's try to use these ideas to model the behavior of particles like free electrons. After all, a wave packet does have a sense of lumpiness like a particle, and evidently it has wave characteristics. Now, what's the significance of this wave number plot down below? Well, wave number is defined as 2 pi over lambda. So let's use the de Broglie formula to change wave number to momentum. If I put in the de Broglie formula, this gives me k equals 2 pi over h times p sub x. The suffix here is because we're measuring momentum in the x direction. But the important thing is because h is constant, this shows that wave number is directly proportional to momentum. So I can relabel this axis as momentum. Now what about the top graph? Well, it's obviously telling me something about the position of the electron. But I must be very careful how I interpret this. What's the connection between these mathematical waves and a real object which has mass and charge like an electron? Well, remember that the experimental evidence indicated that we should think in terms of probabilities. And what quantum theory does is to make a link between these amplitudes of the wave packet and the probability of finding an electron at that position. So that although the electron is somewhere around here, what I can say is that it's more likely to be at this point, where the amplitude is large, than at this point, where the amplitude is small. And once we've made this imaginative connection, there's a lot more that the model can tell us. For example, suppose I know the momentum of the particle very precisely at some instant. Then, as Graham showed a moment ago, that corresponds to an infinitely long wave of fixed wavelength. So I know nothing at all about the position of the particle. And going to the other extreme, if I know the position precisely at some instant, then I need all these momentum components here to construct that infinitely thin wave packet. And at some intermediate stage, you can see that if I know the position of the electron to roughly these limits, I'll call that delta x, and I can define it in some convenient way, then I'll only be able to know its momentum at that instant to within this sort of range, delta px. In fact, there's a simple mathematical connection between these two uncertainties, which can be quite easily derived from the properties of wave packets. It's the famous Heisenberg uncertainty principle. In words, it says that it's impossible to measure both the position and the momentum simultaneously, that's important, with a precision better than the limit expressed here. Now, it's important to realize that this built-in uncertainty has nothing to do with how well or how clumsily we measure these quantities, nor does it represent a deficiency in quantum theory. It's a fundamental limit imposed by nature itself and which you can't get around. So here's another effect for which we have no parallel in everyday experience or in classical physics. In fact, how does the uncertainty principle square up with the everyday world? Well, to have a reasonable chance of potting that brown, I need to know its position, and I want it to stay put while I'm lining up the shot. Well, I think I know its position reasonably well, and it's stationary, which means that its momentum is 0. In fact, isn't delta p 0 as well? And in that case, doesn't delta x times delta p equals 0, violating the uncertainty principle? Well, before I rush to such a rash conclusion, let me just check exactly what the uncertainty principle, this formula here, puts, what sort of limits it actually puts on the precision with which we can measure delta p. In fact, suppose I were able to measure the position to something like the wavelength of visible light, delta x of order 10 to the minus 7 meters, roughly. Then if I put in that sort of number, which is very small for delta x, I find delta px is about 10 to the minus 28 kilogram meter sec minus 1. Well, what does that number tell us? Well, you can check this for yourself, but what it means for a billiard ball is that we'd have to wait a million years before it moved about a millionth of a millimeter. Not much of a movement. In fact, in everyday language, it's perfectly stationary. Once again, then, the ideas of quantum theory are not contradicting the everyday world. It's just that the effects are so small that we're never going to observe them. Let's see if I can pot the brown. Well, no trouble with the uncertainty principle there. But things are very different when we look at electrons.
According to Bohr's model, the electron in a hydrogen atom moves in a circular orbit around the nucleus. And we should be able to measure simultaneously the position and momentum of the electron to any accuracy we like. But the problem is that this flatly contradicts the Heisenberg uncertainty principle, so this model must be wrong. The correct model of the hydrogen atom is based on Schrödinger's equation, which allows us to predict the probability that we'll detect the electron in different regions of the atom. Now, in this particular picture, we can see the probability density when the electron has its lowest possible energy, when it's in its ground state. We really can't specify the motion of the electron around the nucleus, and we just have to live with the uncertainties of quantum mechanics. Quantum mechanics applies across the entire distance speed diagram, but because the value of Planck's constant is so tiny, we normally observe quantum effects only in this region. And in exactly the same way, the special theory of relativity applies across the entire diagram, but because the speed of light is so large, we normally observe relativistic effects only at very high speeds. Well, the quantum effects we've been looking at in this program can all be understood using the Schrödinger equation, which applies equally well to free particles like the electrons in a diffraction experiment and to confined particles like the electron in a hydrogen atom. But there's a problem with Schrödinger's equation. In atomic physics, we often have to deal with particles that are moving at very high speeds. But Schrödinger's equation is not a relativistic equation. It's not consistent with the principle of relativity. What we really need is a relativistic theory of quantum mechanics. And that's one of the main subjects of the next unit.
But I hope this program has given you some insights into some of the basic ideas of quantum theory and has shown you that classical concepts don't carry down to the world of the atom. The golden rule, remember, is beware of preconceived ideas. They can often lead you astray. So, keep an open mind when interpreting what you see, or what you think you see.